Hello, welcome to today's video where we're going to be looking at something called roots of unity, which is a part of the complex numbers chapter within Further Maths A-Level. So the first question we probably have is, what on earth is a root of unity, or what are roots of unity? Well, it's actually quite a simple concept at its heart, because all roots of unity are the solutions to any equation of the format z to the power of n equals 1, where n is any positive integer. And that's really good news, because actually we already know how to solve equations of this format, or at least we do if we've been keeping up to date with the Further Maths A-Level content so far. If you don't know how to solve equations of this format, I do have a video on that, and the link to that will appear on the screen right now. But assume we do know how to solve these sort of equations. Let's do an example. Let's say we're looking at the situation z to the power of 6 equals 1. To find the first root, well, the advice I gave in the last video was you could start by rewriting the number that's on the right hand side in exponential form. Admittedly, that is a bit silly for the number 1, because that would be just 1 lots of e to the power of 0, because the argument is 0 because we are, of course, on the real axis. The positive real axis, more specifically, actually. But then that's useful, because then if you want to find the first root, you just then take the power of 1/6 of both sides, which of course would therefore then lead to e to the power of 0 to the power of 1/6, which is e to the power of 0 by index laws, which is just 1. That's admittedly why I was saying it was a bit silly that we did bother to convert 1 to exponential form for this particularly simple equation, because of course we already could have guessed that 1 would be one of the roots to this equation, because we already know 1 to the power of anything is still 1. But then to find all the other roots, that's when we definitely are going to be using our other knowledge from that previous topic, which is to realize that all the other roots to this equation will all have the same modulus as this first root, so therefore they'll all have a modulus of 1, and then the arguments of all the other roots will be decided by the fact that all the roots are spread, or distributed I should say, evenly across 2 pi radians. So as we've got a power of 6 for our equation, we're expecting 6 roots, so therefore our roots are separated by an argument of 2 pi over 6, or in other words a argument of pi over 3. So therefore to find our other roots, all we're going to have to do is start with the number 1 and keep on adding pi over 3 onto the argument of that number. So that will also get us e to the power of pi over 3i. It will also get us e to the power of 2 pi over 3i. We could also write the next root as e to the power of 3 pi over 3i, but you could alternatively choose to write that as just more simply e to the pi I, or realizing even better that, of course, e to the power of pi I is just the number minus 1, because we've got an argument of pi, we've gone all the way around to being back on the real axis again. And then continue on, there's 2 more roots we can find. We'd have e to the power of 4 pi over 3i and e to the power of 5 pi over 3 lots of I in the power. Cool! So those are the roots to this equation. Those are roots of unity in theory. But so what? Why are we giving a special name to just solutions of an equation when there was lots of other equations of this rough type that we were solving before, but those roots didn't have a special name? Well, it's because once we've found these roots, we can start to see that some very cool patterns start to emerge. The first thing is that we obviously, of course, know that one of the roots of unity is always going to be 1. And that's because ultimately, if we're solving an equation of the form z to the n equals 1, one of the roots always will be 1, because, as we already mentioned, 1 to the power of anything is still going to be 1, so 1 is guaranteed to be a solution. But then, what happens after that is where things get even more interesting. Because if you look at this second root then has a really big impact on all the other roots that follow after it. Because e to the power of 2 pi over 3i could be viewed as e to the power of pi over 3i all squared. Because by index laws, of course, you'd multiply those 2 indices together. And then e to the pi I, well, we already mentioned that's e to the 3 pi over 3i secretly. So actually this could be rewritten as e to the pi over 3i to the power of 3. And then we could also do the same thing with the other roots as well. Basically, all the other roots will just be powers of that second root. So therefore, for our case, the last root we had was e to the pi over 3i to the power of 5. This is not a coincidence, though. These properties all ultimately happen because we're specifically solving an equation of the form z to the n equals 1. That's because, for instance, in our particular situation, where z to the power of 6 equals 1, we knew the first solution was 1, and also we knew all the other solutions also had a modulus of 1 too, for all of our roots. Whereas, if we're solving a different equation that's not z to the n equals 1, let's say we're solving the equation z to the power of 6 equals 64. If we're dealing with that scenario, the problem is our first root will be 2, and all the other roots would also have a modulus of 2 as well. Again, because all the roots must have the same modulus. But that's a problem, because then when we come to find the second root to this equation would be z equals 2e to the pi over 3i. Again, because we got 6 roots and they're going to be spread evenly about 2 pi radians. Each one is separated by an argument of pi over 3i. That's important because now if we start trying to find z squared, we take that second root to a power, the problem is we're not just going to be squaring the e to the power of pi over 3i, we're not just going to be squaring that bit, we're also going to be squaring that modulus too. And the problem is that means the modulus of 2 will now become a modulus of 4. And therefore, unfortunately, this cannot be a root of our equation z to the power of 6 equals 64, because it's now not got a modulus of 2, which we said must be true for all of the roots of the equation that we're solving. So that's the first thing that ends up being quite neat about solving z to the power of n equals 1. The first root has a modulus of 1, and then if you take powers of any complex number that's got a modulus of 1, it will still have a modulus of 1. And yet the other neat fact also comes when we start to look at the arguments. And that all is down to symmetry, or basically the placement of the specific roots when we're solving z to the n equals 1. If we're solving z to the power of n equals 1, we already know immediately the first root is going to be 1, which is on the real axis and therefore has an argument of 0. That means our second root, wherever it is, will be a complex number with an argument that's got an additional 2 pi over n extra added onto the argument we had before. But as the argument we had before was 0, that means the argument of our second root is guaranteed to be 2 pi over n. That's really convenient because it then means that all of the roots will then just have arguments that are just straight away multiples of 2 pi over n, because we started as an argument 0 and we just keep on adding on 2 pi over n onto the argument each time. That means our arguments will conveniently link up with multiples of 2 pi over n, which is then convenient what you would be doing if you then start taking powers of something with a power of 2 pi over n. And so therefore, all in all, this does lead to the very convenient situation where if you're trying to solve an equation of the form z to the n equals 1, where n is any positive integer, it's guaranteed the first root is going to be z equals 1. It's guaranteed the second root is going to be z equals e to the 2 pi over n of I. And we can then refer to that root as omega. There's that lowercase Greek letter written there. And then ultimately it's guaranteed that all the other roots that are the solutions to this equation are going to be just powers of omega. So omega squared, omega cubed, etc., all the way up until you get to omega to the power of n minus 1. You don't go beyond omega to the power of n minus 1 just because if you do, you're then just cycling back to the beginning again and reaching 1. Cool. So that's what we mean when we're talking about roots of unity, and therefore also, as soon as roots of unity are mentioned, this Greek letter omega starts getting referred to a lot. Right. Okay, with that said though, then there's some other interesting properties that also lead from that. So, what are they? Well, the first of which is coming from the fact that we've just mentioned that z equals omega is a solution to the equation of the form z to the n equals 1. Z equals omega is the second root to this equation, going anti-clockwise away from 1 about an Argand diagram. But wait a minute, if z equals omega is a solution to z to the power of n equals 1, it must satisfy the equation. So therefore you must be able to plug it into the equation and make the equation satisfied. So you can, and therefore that partly explains why we don't bother going beyond omega to the power of n minus 1, because if you get to omega to the power of n, it is going to be equal to 1 again, because omega is a solution to this equation. So that's the first neat property that comes from roots of unity. And there's a second neat property that also follows. See, if we have, let's say, z cubed equals 1, we could actually deal with this using just our Maths A-level knowledge to a certain extent. You could start by rearranging it to make it z cubed minus 1 equals 0, and then we already know from Maths A-level knowledge that z equals 1 must be a solution to this equation, and therefore z minus 1 must be a factor. So therefore you could do algebra division to help us factorize z cubed minus 1. If you do that, you would end up with z minus 1, and the factor you'd be left behind with would be z squared plus z plus 1 equals 0. But it doesn't just stop there. You see, if you have z to the n equals 1, and again you know z to the n minus 1 equals 0 is an equivalent version of writing that equation, we know again that z minus 1 must be a factor of this equation, because z equals 1 must be a solution. So again, you can factorize it. And interesting, if you do algebra division with z to the n minus 1 divided by z minus 1, you're guaranteed to get an equation, or a factor I should say, that looks something like this. And therefore, this first factor is where z equals 1 comes from as a solution, and then this other factor is then where all the other solutions come from. In other words, z equals omega, omega squared, so on and so forth, all the roots of unity basically up until omega to the power of n minus 1. But wait a minute, if z equals omega is a solution to the equation z to the power of n minus 1 plus z to the power of n minus 2 plus dot 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 z squared plus z plus 1 equals 0, then therefore again we must be allowed to plug it into the equation and it must satisfy it. So therefore that means we can say that if omega is a root of unity for z to the power of n equals 1, then 1 plus omega squared plus omega cubed all the way up until omega to the power of n minus 1 must come to 0. Cool. There is another way you can look at this property though, and that just comes from looking at it geometrically. Ultimately, if you look at all the roots of unity for a particular situation, and you look at where they're placed on an Argand diagram, the way they're spaced means that if you were to add all the roots of unity together, viewing them a bit like vectors, you realize that all the imaginary components of each root of unity will always cancel out with another one of the roots that we have, because of the even spacing of where the roots are. And therefore, conveniently, if you add them all together, the same thing will also happen with the real components as well. For every complex root we have, there'll be another root that's kind of equally spaced away from the imaginary axis. So therefore, if you add all the roots of unity together, they're guaranteed to come to 0. Cool! So those are two really cool properties that you can get from roots of unity. However, overall, things to bear in mind are that ultimately, if you're just talking about finding roots of unity, it is just solving an equation in the form z to the n equals 1, and therefore that isn't actually anything new. It's just solving the equation in the same way you did before, but just realizing it's going to take less effort to do. But then the properties that we just discovered at the end, then we can do some other things with them, and we'll be looking at that in our next Further Maths A-Level video. Cool. Hope you found this video useful. See you in a future video. Goodbye.